The tremendous blast is a thought that has framed how we decipher the universe, outlining the foundation of modern cosmology. Additionally, Einstein's theory, known as cosmology course reading, suggests that the immense blast was the moment the universe began its development, pointing to the origin of all matter, energy, and existence. This event happened approximately 13.8 billion years ago and led to the colossal universe we observe today. Improvements in cosmology suggest that the colossal blast most likely wasn't the very beginning. Instead, there could have been a stage before the enormous explosion, which was critical in shaping the universe. This pre-stage is referred to as infinite expansion. One of the most fascinating contemporary ideas in cosmology suggests that before the intense heat of the enormous blast, the universe underwent an incredibly rapid and dramatic expansion. During this time, the universe multiplied its size at an astonishingly fast rate. To illustrate how extreme this expansion was, if the universe began smaller than an atom, it would have expanded to an incomprehensibly larger size than the entire observable universe within a tiny fraction of a second, a quadrillionth of a second. This expansion stage didn't last long, yet it played a critical role in shaping the universe. When the inflationary stage ended, the driving force behind this expansion was released into the universe, heating it and creating the matter particles that make up everything we observe today. Some theories suggest that this phase of growth was the precursor to what we call the huge explosion. While the expansion hypothesis is commonly accepted in cosmology today, numerous unanswered questions remain. For instance, we still don't fully understand what initiated this expansion, what caused it to stop, or how long it lasted. Before this expansion, the universe existed in an incredibly dense, small state, often referred to as a singularity. From this point, expansion began, eventually leading to the formation of atoms, stars, and galaxies. The idea of the gigantic blast being the start of everything is compelling, but modern cosmology paints a more complex picture. Some hypotheses suggest that the universe underwent a phase before the enormous explosion, during which expansion caused the universe to grow at an extraordinary rate, by a factor of 1 trillion in an extremely short time. This brief expansion was fueled by a mysterious form of energy that eventually converted into particles, heating the universe and leading to the hot, dense state we now call the Big Bang. While this inflationary stage was cold and empty, it set the stage for the creation of matter and the universe as we see it today. One of the more recent theoretical ideas in cosmology is the concept of timeless expansion. This hypothesis proposes that expansion did not stop all at once but instead ended intermittently, creating a vast range of separate pockets, each potentially its own universe. If this idea is correct, our universe could be just one of many, with an endless number of other universes existing, each with its own unique set of physical laws and constants. This brings us to the idea of the multiverse, the possibility that our universe is one among many, or even an infinite number of universes. If this theory is valid, it could explain why our universe is so finely tuned for life. In a multiverse scenario, every possible combination of physical laws may exist across different universes, and we simply exist in one that happens to have the right conditions for stars, carbon, and life to form. While theories like the multiverse and eternal expansion remain open to speculation, the idea of inflation is supported by strong observational evidence. One of the biggest pieces of evidence comes from the cosmic microwave background, CMB, the oldest light in the universe. The CMB was emitted about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form. Since then, this light has been traveling through space. By studying the CMB, cosmologists can essentially take a picture of the universe in its infancy. This light provides critical details about the early universe, helping researchers understand what happened after the Big Bang and offering strong support for the inflationary model. One of the most significant discoveries came from the European Space Agency's Planck satellite, which captured detailed images of the CMB. These images revealed subtle temperature variations in the early universe that match predictions made by the inflationary theory. The evidence from these studies shows that the idea of cosmic expansion is not just a theoretical concept but a fundamental part of our understanding of the universe's origins. To fully comprehend the Big Bang and what came before it, physicists must reconcile two of the most important theories in modern science: Einstein's general relativity and quantum theory. General relativity explains the large-scale structure of the universe, including the behavior of planets and stars, while quantum theory describes the smallest-scale behavior of particles. To answer fundamental questions in cosmology, such as what the universe is made of and where it came from, scientists must develop a theory that unites these two frameworks. One of the most astonishing aspects of the universe is its vast size. The most distant objects we can see are about 47 billion light-years away, making the observable universe approximately 94 billion light-years across. Given that the universe is only 13.8 billion years old, this may seem paradoxical. How can the observable universe be larger than the distance light could travel in that time? The answer lies in the fact that the universe has been expanding over time. As space expands, distances between objects increase, making distant objects appear even farther away. Most scientists agree that the universe is vast beyond the observable universe, and it is entirely possible that the entire cosmos is infinitely larger than what we can currently detect. Boundless in size. The detectable universe. The entirety of the universe that we can see is restricted by how much time light has required for transportation since the tremendous blast. There might be huge portions of the universe that we'll always be unable to see. While it's conceivable the universe is endless, the inquiry remains. Is it? Anything beyond the universe is uncertain. Most researchers are unsure of their conclusions about this thought. On the off chance that there is no end to the universe, then beyond it, the universe would basically proceed with perpetually. Regardless of whether the universe is restricted, it probably will not make sense to discuss anything prior to it. That would infer the existence of something outside of space itself, which is a property of the universe. So, the possibility of beyond the universe probably won't mean anything in real life. Just as the beginning of the universe is a topic that requires much attention, so too is its inevitable end. The best current estimate is that the universe will keep extending perpetually. This is anticipated due to a bizarre peculiarity known as dark energy, which is causing the universe's expansion to rapidly advance. Before the discovery of dark energy, researchers believed that the universe's expansion would eventually slow due to the pull of matter's gravitational force. There was even a possibility that the universe could quit growing and start contracting, leading to a big crunch. However, dark energy appears to be tearing the universe apart more and more swiftly. If this rate of acceleration continues, the universe will never stop expanding. Eventually, galaxies will float so far apart that they will separate entirely. In this scenario, the universe would become cold and lifeless. Stars would burn out, planets would drift into darkness, and matter would eventually decay. This is known as the Big Freeze or heat death of the universe. The narrative of the universe. From the massive explosion, Big Bang, to its most improbable outcomes, the story of the universe is one of the most important and intricate in science. While we've learned an extraordinary amount about the origins of the universe based on the theory of expansion and the study of the cosmic microwave background, many questions remain unanswered. What caused expansion to start and end? What lies beyond the visible universe? Does the multiverse exist, and if so, how many other universes are there? As research continues, scientists are utilizing advanced technology and theories that link quantum mechanics with general relativity. Without a doubt, we will gain deeper insights into these mysteries. The journey to comprehend the universe continues, and every discovery brings us one step closer to answering the ultimate questions about our existence. The study of the structure and origins of the universe is more than just a scientific pursuit. It also raises profound philosophical questions about reality and our place in the cosmos. The nature of dark matter and dark energy. One significant topic in cosmology is the nature of dark matter, which is believed to make up about 27% of the universe's total mass energy content. Unlike normal matter, dark matter does not emit, absorb, or reflect light, making it invisible. It is only detectable through its gravitational effects on visible matter. Understanding dark matter is crucial for grasping the formation and behavior of galaxies. Ongoing studies and observations have provided insights into dark matter's properties. However, its exact nature remains elusive. Several candidates have been proposed, including weakly interacting massive particles, WIMPs, axions, and other exotic particles. But so far, no direct evidence of dark matter particles has been found, and the search continues. Scientists are using a combination of terrestrial experiments, astrophysical observations, and computer simulations to model how dark matter shapes the large-scale structure of the universe. Another key area of exploration is dark energy, the force driving the accelerated expansion of the universe. Dark energy makes up about 68% of the universe's total energy content. Its discovery was surprising and led to multiple theories, including the cosmological constant and dynamic fields like quintessence. Understanding dark energy is crucial because it will determine the ultimate fate of the universe. Researchers are studying its effects on cosmic structures and trying to determine whether it remains constant over time or evolves. The structure and evolution of the universe. Beyond dark energy and dark matter, the large-scale structure of the universe offers significant insights into its history. Observations of the cosmic web, a vast network of galaxies, clusters, and filaments, have revealed how matter clumps together under the influence of gravity, forming the complex structures we see today. Supercomputer simulations help scientists understand how these structures evolved over billions of years. Meanwhile, fields like astrobiology are merging with cosmology as scientists seek to understand the conditions necessary for life on other planets. The discovery of exoplanets, planets orbiting stars outside our solar system, has accelerated in recent years. Thousands have been identified, and some exist in the habitable zones of their stars, where conditions may allow liquid water to exist. By studying these distant worlds, researchers hope to learn more about the potential for life elsewhere in the universe. Fundamental physics and cosmology. The role of fundamental physics in cosmology cannot be overstated. The quest for a unified theory that links general relativity and quantum mechanics continues to challenge physicists. Theories like string theory and loop quantum gravity aim to bridge these two fields, offering explanations for phenomena like black holes in the early universe. As technology advances, so does our ability to study the cosmos. Space telescopes such as the James Webb Space Telescope provide unprecedented insights into distant galaxies and cosmic events. These revolutionary observations are helping us unlock the secrets of the universe's formation, evolution, and ultimate fate. The endless pursuit of knowledge. The study of the universe is a complex web of scientific inquiry and philosophical reflection. From the fundamental forces that shape cosmic structures to the search for extraterrestrial life, our exploration represents humanity's relentless curiosity and perseverance. As we seek to answer these profound questions, we gain a deeper appreciation for the vastness and complexity of the universe, reminding us of how much there is still left to discover.